You're Jeffrey, right?
Yes. I haven't got my Pokemon name yet. So.
We were sending him out. It's been a while. Oops, I'm sorry.
It's fine.
Okay, can you hear me, guys? Okay. You know the rules. Please shut your laptops, turn down your phones. Everybody except the TAs, that is, they get to keep their laptops open because they monitor Piazza and Zoom. Get your name tags out. My clicker is run out of battery, so I've sent my TAs out for a new one. And until I get that, I'm going to be right here clicking the mouse. But once I get my clicker, I'll be walking up and down, which means that if you have your laptop or phone open, I'm going to see that, right? There are some empty seats here. You don't need to stand up there, so you can just come in. All right. Morning, everybody. And thanks for making it to an 8 a.m. class. This gets harder as the semester progresses because it gets colder and darker in the morning. Do you mind shutting your laptop? So yes, all of you guys shut your laptops, please, right? So we sort of looked at what multilayer perceptrons were in the first class. Now, what can they represent? That's what the topic of today's lecture is. So we're going to look at what neural networks can represent and what are the restrictions in terms of the depth, width, and the activations of these neurons. Now, here's a quick recap from the last class. We saw that a lot of tasks that we thought were previously considered to be in the domain of human expertise, like playing games, painting pictures, answering questions, what have you, these have now been, it has been possible to automate them using deep neural networks. And we're here to find out how and why, right? So for that, we first have to understand what are these neural networks. In every case, the neural network is this box. It's a function that takes an input and produces an output. And when we perform different tasks, what all we're really doing is changing the input and the definition of the output that we would get in each case. And in the case of human beings, these functions are computed by the human brain. So if we want to be able to perform these tasks automatically, it kind of makes sense that we want to mimic what happens in the human brain. And so in their basic form, neural networks mimic the network structure of the human brain. We also saw that your brain is basically a very large and dense network of very simple computing elements, namely the neurons. And so our artificial neural networks mimic this structure. They too are large, dense networks of very simple computing elements, which we called perceptrons. And the perceptron is some kind of an approximation of what happens in the human brain itself, in biological neurons. Here's what we said it looked like. Let me just shut this. In the simplest form, a perceptron had a bunch of inputs, and it computed a weighted sum of these inputs. And if the weighted sum of the inputs exceeded a threshold The output was 1, otherwise it was 0. So now, just for and those of you who are electrical engineers, you'll recognize these as threshold gates. And now, just for future reference, I can rewrite this thing slightly differently. I can write this as summation wi xi minus t greater than 0. These two you will see are the same, exactly the same statement. Or I can write this as theta of summation I wi xi minus t, where theta of anything equals 1 for z greater than 0, 0 else. All three are the same statement, right? And finally, so I can write this again as z equals summation I wi xi plus b. We call this a specific kind of operation. What did we call it? It's an affine function. And we can say y equals theta of z, where? So this guy is a thresholding operation. It just checks if the input is positive and outputs a 1 if so, otherwise not. And so using this simple restatement, here's what a threshold unit looks like. It first computes a z, which is an affine function of the inputs, and then applies a threshold function to this affine term z. Now, which means again that you can, thank you. So this is what I mean. Pointing is going to become so much simpler. That screen is way too high for me, so I need things to point, right? Okay, great. And so now I can rewrite this like so. I first compute an affine term z, and then pass that affine term through a function theta, which just basically determines if the input is positive or not. And once I can, and so what does theta of z look like? Theta of z looks just like this, right? It's, if this is z, for z negative, the output is 0. For z positive, the output is 1. So we first computed the affine term z and then put it through this threshold function. But then once I decided this is what I'm doing, I'm first computing an affine term and then putting it through a function, which we call an activation. Then we can change this function itself, say for something like this, which is a smoother version of the threshold. So that's a squashing function instead of a threshold output. This kind of perceptron, the function itself is called a sigmoid, the one that's a smoother version of your threshold. But once you realize that you can change the function to something, other kinds of functions, we can even replace it with yet other functions, like the tan h, which is just the sigmoid scaled a bit and shifted to be centered at 0. Or the ones to the right, the rectified linear unit, is one where the output is 0 if the input is negative, and the output is the same as the input when the input is positive, or the soft plus, which is a smoother version of it, right? All of these things can be done. Now, for the purpose of today's lecture, we're going to stay mostly with the threshold activation, which is this guy here, because it sort of simplifies explanations, right? So here's your very first poem for the day.
Also, don't forget to do the lecture quote, attendance quote if you haven't done so.
Okay, that should be easy. I think most of you should be done by now. Let me pull up some random names. Okay, someone here. Deepam is the first one. Affine or not? Linear.
Yeah, it's a linear combination of x.
It's a linear combination of x and y. And Noah, what about the second one?
No.
It's not a. Is it a linear combination of x and y? Yes or no? What do we say? It's affine. Why?
Because we are adding a constant.
We're adding a constant 4, right? And Joshua, what about the third one?
Yes.
This is an affine function because the bias could be 0. And you there, you don't have a name tag. First, do you mind shutting your laptop? Right, okay. What about the fourth one? Affine. Okay, so you get the idea. What's an affine function? What's a linear function, right? So these three are right. Anyway, let's move on. So that was what we saw in the last class. Now, what is a multi-layer perceptron? A multi-layer perceptron, this is our way of emulating the brain, as we said, but it's basically a network of perceptrons where you have some perceptrons which feed other perceptrons, which feed other perceptrons, and eventually you get an output. And we can think of these as having been arranged in layers where each layer of perceptrons feeds all subsequent layers. Now, what is a layer? We'll get to that shortly. So when we began speaking of neural networks, we speak of deep neural networks. How do you understand deep in this context? Anybody? Yes?
A lot of layers.
How many a lot?
Yeah, how many?
So what is a lot?
I think it depends on the case. I don't know. Like, I feel like there's not like a set definition.
Yes.
Any hidden layers present?
Any
I think
hidden-
it's the number of neurons in each layer.
Okay, so there's actually a formal definition. Jeffrey, go ahead.
Is it like when you have more than one hidden layer?
Exactly, right? But let's get to this, right? So here's how it is defined. Now, how many of you are familiar with what a directed acyclic graph is? Almost everybody must be, right? So what is a DAG? Yes.
A DAG is a graph that is directed edges from one node to another, but it doesn't have a.
So it's any kind of graph where you have nodes and every edge has a direction and nothing comes back. So there are no loops, right? And in a DAG, you're going to have a bunch of nodes which are sources, which have only outgoing edges. And you have a bunch of nodes which are sinks, which have only incoming edges. The depth of the graph is the length of the longest path from a source to the sink. So what's the depth of the graph to the left in my picture? 2, right? Although there is a path of length 1. What about the second one, the one to the right? What's the depth of that graph? 3, right? Because the longest path is 3. Although there are paths of length 2 and length 1. So in a neural network, I can have several inputs which feed one set of neurons, their output feeds the next set of neurons, their output feeds the next set of neurons, and so on. And eventually the output is a sink, the input is a source, and so the network is going to have a depth, which is the length of the longest path from the input to the output. So what's the depth of the network over here? Anybody? What's the depth of this one? Someone, come on, that's easy, please. 3, okay. What about the one to the top right? If each box is on as a set of, that you were saying 2? Okay. And the one to the bottom right? 4. Okay, so you get an idea of what depth is. But we're speaking of layers. What do we mean by a layer? Anybody? Yes.
So if you start from the source, the way you can reach that perceptron to a path is like it is the same in doing this layer.
Absolutely, right? So a layer is the set of neurons that are all the same depth with respect to the input. And so you see this network over here? Can someone identify all the neurons in the first layer? Anybody here? Well, if you guys won't speak up, I'll pick up, point to people. So, someone? Which are the neurons in the first layer? Yes.
I think there's 6.
6 neurons in the first layer. Are you sure?
Yeah.
This is the input, okay? So this is let's call this the 0th layer, right? So, okay, you don't have your name tag out. What's your name?
Arvin,
Arvin. So, which are the neurons in the first layer? Can you tell me?
I would say 3.
Which ones?
First,
Yeah.
the vertical ones.
These ones?
No. I'm so sorry. So I would think that it's 3. How do I find?
So this is the 0th layer, right?
Yeah.
Okay.
First, okay, 2.
So here are the ones. So all the red neurons are the ones in the first layer. They're all depth 1 with respect to the input, right? All of the green neurons are the second layer. They are depth 2 with respect to the input. The yellow ones are the third layer. They're depth 3. And the blue ones are depth 4. So as you can see, it doesn't matter how I draw it. There's a very clear and formal definition for what it means, what a layer is. They are the set of neurons that are a fixed depth, a specific depth with respect to the input. And so when we speak of a deep neural network, we are speaking of a neural network whose depth is at least 3, which means that it has at least 2 hidden layers and an output layer. Okay? So now, what's a multi-layer perceptron? Yes.
On the other slide, aren't the green ones only 1 away from the input layer? So
How did we define depth?
I thought it was the minimum
It's
distance from the input.
what was the depth here?
Oh,
Right, is the longest distance. It's not the minimum distance. Okay, so yes.
Is there significance to calling 2 or more layers deep, or is that just convention?
Just convention, right? So now there is a significance to it. We'll get to that later in the lecture, and you can remind me if I don't answer you, right? So anyway, inputs, as we saw in the last class, the inputs to a multi-layer perceptron can be real or Boolean. The outputs can be real or Boolean, and you can have more than one output for any given input, although the figure to the left has only one output, the one to the right has multiple. Now, what can this network compute? In other words, what are the kinds of input-output relationships it can model? We already saw some of this in the last class, but let's revisit. We saw that MLPs can compose any Boolean function. So we called MLPs universal Boolean functions. Does that mean the same MLP can compute every Boolean function? So what did we mean by that? What did we mean? Yes.
For every Boolean function, you can construct like an MLP to solve it.
So for any Boolean function at all, I can compose an MLP that will compute it, right? We also saw that MLPs can compose category functions, classifiers, classification boundaries. And these are universal classifiers. Again, what did we mean by saying it's a universal classifier? Yeah.
It can compose like several decision boundaries together into any kind of decision boundary.
You can approximate pretty much any decision boundary with it to arbitrary precision, right? And we also saw it can compose real valued functions in the same way, right? You give me a real valued function, I can compose an MLP that approximates it to arbitrary precision. So they are universal function approximators. What are the limits? That's what we're going to see. MLPs as universal Boolean functions and the need for depth. MLPs as universal classifiers and the need for depth. And MLPs as universal function approximators and the need for depth. So let's consider this first topic. How well do MLPs compose Boolean functions? Before we even talk about MLPs, let's talk about the individual perceptron, right? Now, I'm using the same convention as in the last class. The threshold is inside the circle. The weight is above the edge. And so what was the function that the perceptron on the top left computed? And, right? The one on the right? Nor, and the one at the bottom? Or, right? But it's not just simple Boolean functions that a threshold gate can compute. It can compute something far more complex. So here is a perceptron which is going to fire if and only if the first L inputs are all 1 and the remaining inputs are all 0. Can you tell me why? Anybody? Yes.
If the first, notice that the threshold is on, so it only fires if and only if the first L of X are going to be on because they each have value 1. And if any one from X plus 1 to Xn are activated, then that'll necessarily make it less than L and so on.
So basically, if the first L are all 1 and the remaining are all 0, the total weighted input is L. If you flip any of the first L, the total weighted input is going to decrease. If you turn on any of the ones at the bottom, because those have a weight of -1. Once again, the total weighted input is going to decrease. So the only condition under which it's going to fire is if the first L are 1 and the remaining are 0. In fact, you can set it up to pick any specific pattern and fire only under this pattern. And the way you do it is these guys would have weight 1, and these would have a weight -1, and your threshold is right, and that's going to give you an AND. So this is a universal AND gate. Here's one that will fire if any of the first L are 1, or if any of the subsequent inputs are 0. So can someone explain to me how that happens? Over here. Anybody? Yes.
Well, let me try doing the math. If all of those ones are 1, all the green ones are 1, and all of the red ones are 0, I think what happens is that I think it becomes like n minus.
So okay, you're right. So let me answer, right? So there are L entries which are in red, and there are n minus L inputs in green, right? So if all the red inputs were 0 and all the green inputs were 1, then you're going to have n minus L inputs which are 1, but each of them has a weight of -1, so the total input is L minus n. And you want the threshold to be greater than L minus n. So if I make the threshold L minus n plus 1, if I flip any one of these inputs, which means if any of the green ones become a 1, or if any of the any of the green ones become a 0, or if any of the red ones become a 1, it's going to match. Yeah. Yes.
So the L minus n plus 1 is the threshold.
Yeah.
And the 1 and -1 are the weights.
Yeah.
Okay.
Right. So you can see how this works. But then you can do something much more fancy, right? This you can do with a conventional Boolean gate. But here's a situation where I will have an input, and this unit will fire if any k, at least k of the inputs are 1. Can you see how, right? If at least k of the inputs are 1, it's going to fire. It's a majority gate, depending on the choice of k. If you want to construct a Boolean circuit, not something that uses threshold gates, that computes the same function, how many gates do you think you would need? It turns out that if you want to do this using Boolean gates, it's going to need many, many, many more gates, an exponential number of gates, because you're going to have to tag every pattern for which you want the output to be 1. And so that's why these threshold gates, a single threshold gate can compute a Boolean function that would require an exponential number of Boolean gates, which is why they thought these things were incredibly powerful. And so, this led to a lot of the fallacies about this being a universal computer. But we found it's not. This simple thing cannot compute an XOR. Yeah.
Just a quick question on the L and N. Does the N, like if we go to the last slide, does the N represent the total number of input?
N is the total number of inputs.
Okay.
Right? So N is over here. Now, we saw that this cannot compute an XOR, right? But then we could compute an XOR using a network of these guys. How did we do that? Anybody? So we did this by just doing, just replicating the Boolean function that's an XOR. We had one for the OR of the 2 inputs, another for an OR of the negations of the 2 inputs, and then we ANDed the lot. And so we have an XOR. It actually turns out that these are threshold gates. They're more powerful than standard Boolean gates. You can do this with just 2 gates, 2 threshold gates, right? And this is going to give you an XOR as well. And we will see why later in the class. But anyways, so they're more powerful. You can reduce the number of gates, but you cannot get an XOR with fewer than 2 perceptrons, okay? But once you realize that you can compose things like Boolean gates and some things which are a little more complex than Boolean gates, you can actually compose a multi-layer perceptron to compute pretty much any Boolean function, which is why we said MLPs are universal Boolean functions. But now, consider this. This picture to the left, how many layers does that network to the left have? Anyone? 2? How many layers does it have? 3 layers, right? What's the depth of the network again? 3, right? So, or here's a network which has many more layers. The depth is, it's a pretty deep network, right? So in the examples that I showed you, we are able to compose pretty much any Boolean function, but the network has many layers. Suppose I said you're not allowed to make the network deep, which means you have only one hidden layer. In that case, can I compose all Boolean functions if I'm only allowed one hidden layer? What do you think?
No.
No? So how many of you think no? Raise your hands. And how many of you think yes? And some of you have, how many of you have no opinion? You have this null set which doesn't have an opinion, doesn't think yes, and doesn't think no. That's not right. So let's try this again. How many of you think yes? And how many of you think no? Okay, and that lady there has no opinion either way, right? So guys, raise your hands, okay? Anyways, my claim is that I can do this with one hidden layer. Let's see why, right? A Boolean function is just a truth table. I have a set of inputs and I have an output. And so I can list the output with respect to every single pattern of inputs. And if I have n inputs, this table is going to have 2 raised to n rows, but I don't need to list all of them. I only need to list the specific entries for which the output is 1. The rest are implicitly 0, right? So this truth table is a Boolean function. Now, once I give you a Boolean function of this kind, then what does that first row in the table tell me? Anyone? What does the first row in the table tell me?
For that pattern, output 1. For that pattern of 0s and 1s.
For that pattern of 0s and 1s. So when I have x1 is 0, x2 is 0, right? x3 is 1, x4 is 1, x5 is 0. So this is going to give me an output of 1. Alternately, I can say not x1 is 1, not x2 is 1, x3 is 1, x4 is 1, and not x5 is 1, right? And so that first row gives me the clause not x1, not x2, x3, x4, not x5. This making sense to you guys? And so I can write one such clause for every row in the table. This first row over here tells me that first row, first entry captures the first row. The second one captures the second, the third captures the third, the fourth, fifth, and the sixth. And we know that each one of these clauses can be captured using a perceptron. And then I can just OR the lot. And so it doesn't matter how complex the truth table is. I can always build a one hidden layer network which will model this Boolean function exactly. That making sense to all of you guys, right? So yes.
Is that why they call a one hidden layer neural network a universal approximator?
A universal Boolean function. Yes, actually it is a universal approximator. We'll get to it more, right? So yeah.
From the question that you mentioned, is this why for deep networks we have to have to open?
No. Okay. So we'll get to that. But then, okay, so this is what is called a disjunctive normal form. You have the ORs of many ANDs. And so when I express the Boolean function in DNF form, disjunctive normal form, that's the number of clauses in this form tells me how many neurons you will need in the one hidden layer, right? So this is fine. A one hidden layer MLP is a universal Boolean function. But then, if I want to do this with just one hidden layer, what is the number of neurons that I'm going to require in that one hidden layer in the worst case? N plus 1? No. Jeffrey?
You mean the hidden layer, right?
Yeah.
I think it's going to be the number of input combos that have the value of 1.
So what's the worst case?
How many?
Yes.
The number of this.
It's exponential and n, right? Let me see why. How many of you are familiar with Karnaugh maps? Raise your hands if you know what a Karnaugh map is. That's a pitifully small number, right? So a Karnaugh map is a topological way of representing inputs. So this picture to the left represents a Boolean function of 4 inputs, w, x, y, and z. So the 4 rows represent the 4 combinations of wx. The 4 columns represent the 4 combinations of y and z. And what you'll observe is that if you take any 2 columns, they only differ in 1 bit. If you take any 2 rows, they only differ in 1 bit. And moreover, this is actually a torus. It's not a rectangle, a square. The uppermost row differs from the lowermost row by only 1 bit. The rightmost column differs from the leftmost column by only 1 bit. So any square over here represents one particular bit pattern. So this guy for here, for instance, represents the input pattern 1, 1, 1, 1. The highlighted boxes show the input combinations for which the output is 1. The rest of them show input combinations for which the output is 0. So for this particular truth table, how many different inputs generate the output 1? Anybody? Myra? 7 of them, right? So if I were to build a very simple, very naive DNF formula, how many clauses would it have? 7, right? But then once I arrange things in this manner, you can begin grouping them up like so, right? All of these output are 1. So what does this mean? It tells me it doesn't matter what w and x are. Those 4 together become 1 clause, right? Similarly, these 2 both generate the output 1, which means it tells me that the value of z does not matter. I can group them up, and so now I'm just going to end up with the clause not wx, not wy, not y, right? Similarly, these guys both produce the output 1, which means it tells me it does not matter what the value of w is. And so once I begin grouping things together, I can produce a much smaller number of groups, and so the actual DNF formula that I get is very small. And this is how we actually reduce the size of Boolean functions and make small networks. So the worst case scenario is the smallest is a truth table where the smallest network, set of groups is as large as possible. What would this be? What kind of Boolean function would not let me, cannot be reduced any further by grouping? Anybody? So what arrangement of 1s and 0s simply cannot be reduced further? A checkboard pattern. There's no way for me to actually group anything, right? So for this guy, how many clauses will I have in my DNF formula? Over here, for this one. 8, right? So here's a 3-dimensional Karnaugh map. It has 6 variables. So 6 variables will give me 64 combinations. But again, it's a checkerboard pattern or a checker cube pattern. So how many clauses will my DNF formula have? 32. Can I reduce it by grouping? There are no two neighbors which have the same color. So I can't reduce it any further, right? So to generalize, if I have n inputs, what is the worst case number of clauses in the DNF formula? Yeah.
2 to the power of n minus 1.
2 raised to n minus 1, right? So we'll require 2 raised to n minus 1 perceptrons on the hidden layer. It's going to be exponential and the number of inputs, right? So here's your second point. A bunch of folks at the back. If you don't mind, I'm going to talk from the back for a bit because these guys don't get to hear me. Right. Okay, does somebody want to answer this question? How many will we need? Yes?
512.
512, is that right? Yeah. And that's because you have 10 inputs. 10 inputs are going to give you 1024 combinations, half of them are 1, right? So this is because I had only one hidden layer. If I allow myself to have multiple hidden layers, what is the size of the network I will require? Can somebody tell me? But do you mind shutting your laptop? Yeah, thank you. Yeah, no, that's fine. No, I'm telling this. Okay, so how many neurons will I require if I allow multiple layers? What is this function? Anybody? What is this function? This is an XOR, right? An XOR is a classic function where every time you flip one of the bits, the output changes. That is the definition of an XOR. So the figure to the left is a W XORed with X, XORed with Y, XORed with Z. The one is, again, an XOR of 6 variables. And for a single XOR, how many neurons did we need? 2, 3 or 2, right? Let's assume the 3. This is an XOR, right? So this guy can be composed like so. If I use the 3 perceptron variant of the XOR, I can do this with only 9 neurons, right? Okay, 9 is greater than, as the same. I didn't really gain very much, anything, by using this network instead of just a one hidden layer. But in this case, there are 1, 2, 3, 4, 5 XORs. So I need 15 neurons. Whereas if I did this naively, I needed 32, right? Can someone tell me the generic formula for how many neurons I would need if I had n inputs in this case? Yeah. 3 times n minus 1, because every new variable is going to give you one more XOR, right? So the XOR of n variables requires 3 times n minus 1 neurons. Whereas that's because I let my network be deep. I just kept adding more layers. Whereas if I kept it flat, a single hidden layer, I needed 2 raised to n minus 1 neurons. And so here's the difference. If I have only one hidden layer, I'm going to require an exponential number of neurons. If I let the layer be deep, the number of neurons required is linear in the size of the input. And you can see the difference can be tremendous as n increases, right? That's why we need depth. So how many layers will I need in the best case? What is the smallest number of layers I can get away with? Anyone? So here's how I can do this, right? So if I have, let's say, the thing is that the XOR is associative. And so if I have, where's the check? If I have an XOR of X1, X2, this is just one XOR. This thing has 3 neurons, right? But then if I have an XOR of X1, X2, X3, and X4, XOR is associative. What I mean by this is that now I can XOR these 2 guys. This 2 needs 3 neurons. And then I can XOR these 2. And this is going to give me the final XOR, right? So now suppose I had 8 inputs. So X5, X6, X7, X8. So then I can XOR these 2 guys. I can XOR these 2 guys. So now after one set of XORs, my 8 variables became 4. Then those 4 variables can again be XORed pairwise. I'm still left with 2 variables. And now these 2 can be XORed. And I got my final XOR of all 8 variables. How many layers did I need?
6.
3 over here, right? So it's going to be log base 2 of n layers. The number of layers is going to be 2 times log base 2 of n, because you need 2 layers for each XOR, correct? And so by pairing terms in this manner, I can get this with 2 times log base 2 of n. I cannot go below that and have a finite, linear number of neurons, okay? Yeah.
Going a little faster, so I just want to ask a few. I'm going to make the clarifying question very quick. So let's see. So the main takeaway we should get from the Karnaugh map, it's that like the way we arrange the Karnaugh map, like at most 2 to the power of n minus 1 combos can be a value 1 because that's the checkerboard case, the XOR case, right?
Yeah.
And the second one I want to ask is that like if you have layers, then you only need 3 n minus 1 perceptrons because like and the reason why is because it's because of the number of layers, right? Because of the number of layers, you only need that many perceptrons.
Because you can keep pairing up things. And so you're doing this one XOR at a time, right? And furthermore, I can just group these XORs. I can do this by pairs. And so I can get away having 2 times log 2 of n layers. This is the smallest number of layers. Is there any way I can go below this and still get an XOR in this manner? There's nothing, right? Pairing is the best you can do. And so if the number of neurons must be linear in the size of in n, then there is a function of the input. And so the number of layers you need depends on how many inputs you have. And if you have those many layers, then your network is going to be linear in the number of inputs. Otherwise, it's going to grow. Why so? So again, observe that this is an XOR of 8 inputs. But if I call this A1, A2, A3, and A4, this function is simply A1 XOR with A2, XOR with A3, XOR with A4, right? So which means from this point on, I still have an XOR. If I call this B1 and B2, then from that point on, I still have an XOR. So no matter where you slice it, the subsequent network is XOR. And so if I just say that you're only allowed to have k layers in your network, that means that the first k minus 1 layers, or k minus 1 over 2 layers, can each reduce the number of variables by a factor of 2. But at that point, you're still left with an XOR problem. And after that, you have only one more hidden layer. It's still going to be exponential by the number of terms that are remaining. And so if you have a fixed number of layers, the number of neurons that you will require to compute the function eventually is going to be exponential in the size of the input in the worst case, right? Why did I choose an XOR as my example? An XOR is a horrible function. If you get 1 bit wrong, what is your error rate? It's going to be 50%. It becomes random. If you just get 1 bit wrong, the XOR is going to be completely random, right? It's going to be wrong 50% of the time. It's a binary function. You can't be worse than 50% wrong. So a network with fewer than the minimal number of layers is going to be exponential in size. If you decide to use a smaller number of neurons because you can't afford it, in the worst case, you're going to be so wrong that you couldn't be more wrong, right? And so a network with fewer than the minimum number of layers and fewer than the minimum number of neurons cannot model the function. Now, this is the worst case. In other cases, you can sort of approximate it, but this is just to give you an idea, right? Any questions? Yeah.
When you said that we need 2 log n layers, in this example only I see a depth of 3, so and there were 8 inputs.
Yeah.
Why is it not log n? Because we are halving.
So each of these is actually 2 layers, right? There's an XOR.
Okay.
That's why. Yeah.
And the reason why I use XOR is provide kind of worst case Boolean function.
Yeah, so actually an XOR is not the worst case Boolean function. XOR is a very nice function for threshold perceptrons, but I'm using the Boolean model over here just to give you the idea. There's a very nice paper by Claude Shannon, which uses a save mechanism to decide what is the smallest number of neurons you will require. And it turns out that of the super exponential number of functions that you can have for n Boolean inputs. If I have n Boolean inputs, how many different functions can I have? Anybody? For n Boolean inputs, how many different functions can I have? 2 raised to n?
N factorial.
N factorial. Anybody else? Come on, guys, you know this. Tell me. So if I have, how many rows will the truth table for an n input function have? How many rows? 2 raised to n. How many values can can the output take for each of these rows? 2, right? So what is the total number of truth tables you can have? 2 to n. So if I have n inputs, then I can have 2 raised to n rows. Each of these can be 0 or 1, right? So it's 2 raised to, so 2 times 2 times 2 times 2 times 2 times 2 times 2, 2 raised to n times, it's 2 raised to 2 raised to n. That's how many different Boolean functions you can have with just n variables. And it turns out that the vast majority of them will require an exponential number of neurons. If you just randomly pick one of these functions, it's the probability that it's going to require an exponential number of neurons approaches 1. Okay, so anyway, so in summary, an MLP is a universal Boolean function, but it can represent a given function only if it is sufficiently wide, because if you even reduce one neuron, in the worst case, you will be wrong half the time. It has to be sufficiently deep. For our XOR, if you're using the Boolean structure, you need at least 2 times log n layers. And you can trade off depth for width by saying I'm going to have fewer layers, but my layers are going to be very wide. But still, there's always a minimum number of neurons that you will need. So in the optimal width and depth depend on the number of variables and complexity of the Boolean function, where by complexity, I think of it in terms of the minimal number of terms that a DNF formula for that Boolean function will require, right? So the story so far, multi-layer perceptrons are universal Boolean machines. A network with a single hidden layer is a universal Boolean machine, but a single layer network may require an exponentially large number of perceptrons. Deeper networks may require far fewer neurons than shallower networks to express the same function. It could be exponentially smaller. Any questions? Yeah.
Go back one slide. I just want to see the slide. Oh, okay, never mind. I thought you skipped slides because I remember in the Piazza or one of the.
So you can look at the slide numbers. There are hidden slides. Yes.
Yeah. I'm just wondering.
So in the trade-off between width and depth, so we see it as a trade-off between time complexity and space complexity. And in that case, can we consider parallel as well, or?
So the point is, if you go for any, again, in this particular example, if I take one layer off, the width explodes exponentially. So it is actually, if you think of it in terms of parallel computation, if you think of it as time complexity given infinite compute units which can compute in parallel, then you end up with space complexity because the number of variables you have is going to really blow up. Yeah. Let's get back to that. Yes. There's a limit to it, but yeah. You prefer depth over width, and let's see. So MLPs are universal Boolean machines. Even a network with a single hidden layer is a universal Boolean machine, but a single layer network may require an exponentially large number of perceptrons. Deeper networks may require far fewer neurons. So deeper is better than wider, but again, there are limitations, right? So we've looked at Boolean functions. What about classifiers? We saw this again in the last class. Yeah.
Is there any advantage of having more than 2 times log base 2 to the n layers?
So that's for the Boolean case, no, right? The more generic case, you only get approximations. So again, for the MLP as a classifier, we saw how MLPs can form arbitrary decision boundaries, right? So a decision boundary is some region of the input space that you want to cordon off, and you have the output be 1 inside it and 0 outside. And we saw how we could do this with a linear, with just using threshold unit perceptrons. So a threshold unit perceptron has the structure, the output is going to be 1 if the weighted sum of inputs exceeds a threshold, and 0 otherwise. The boundary is where summation I Wixi is exactly equal to t. This is the equation for a hyperplane that doesn't necessarily go through origin. And so a single perceptron using a threshold activation captures a Heaviside function, which is 0 on one side of this hyperplane and 1 on the other side. And so once we have this, you can actually see why you can get an AND gate or an OR gate. You can see why you can get a majority gate, why you can get a negation, but you cannot get an XOR. Why could we not get an XOR? The XOR function is shown to the right. The diagonal is where the output is 1. The other diagonal is where the output is 0. To capture the XOR, you need to go up and then come back down. Whereas a perceptron gets only one boundary. It doesn't get two boundaries. You cannot model an XOR, right? Easy to prove. Okay. So here's an expo. So this is an easy one. Can I pick one of you? I don't see your name, the lady to the extreme left. What's your name? All right, Nikita, huh? What's the answer? Yes. True. Does everybody agree? Is this true? All right, shut your laptops, please. This is true, right? An XOR network needs 2 neurons and 1 out hidden neurons. You actually need at least 2 neurons. You need 2 layers because each layer captures one of these boundaries. And so that's why the XOR network has 2 layers. Okay. And then we saw how we could use this to compose complex decision boundaries, like in the case of this double pentagon. Now, this pentagon. Now, before I continue, someone asked me a question after the last class. If I have, where did I keep my chalk? Okay. If I have this perceptron, which is summation Wi xi greater than t, and so there's this has a boundary. On which side will the output be 1? Right. So now if you look at this, I can write this as W transpose X, where W is the vector of weights, X is the input. And what is W transpose X? It's norm W, norm X cos theta, right? So if your weight is this way and your X is this way, there's an angle between the two, right? And if the angle is less than 90 degrees, that's positive, otherwise it's negative. And so it's going to be 1 in the side of the W, and it's going to be 0 on the other side. Just for clarification, right? And so here, we saw how we could compose this pentagon. I have 1 perceptron for each of these boundaries. And then I finally OR the lot. And the only region of the input where all 5 of them output a 1 is inside the pentagon. So the final perceptron can just take a direct sum of the 5 outputs, compare that sum to a threshold of 5, and I get a pentagon decision boundary. Now, suppose I compare it to a threshold of 4, what would the decision boundary look like? Anybody?
Star.
It's going to look like a star, right? Now, so it's not like the decision boundary is always convex. You can get crazy decision boundaries, but it's still, this thing captures it, right? And we saw once we do this, we can figure out how to compose more complex boundaries like this double pentagon. I would just have 1 subnet for the first pentagon, second one for the second pentagon, and then a final output, right? So and what we can see is that once I do this, I can compose arbitrary decision boundaries like these guys. I just decompose them into many small pentagons or many small polytopes, have 1 subnet for each of these polytopes, and then I OR the lot. How many layers does this have? 3, right? This is the reason why we like this as some sort of a threshold. I can take any odd function And I can compose it to some precision using 3 layers, yeah.
Is there a way to know like the best, for the minimum amount of shapes needed to make it work?
I don't know the function beforehand, so you're asking a complex question, right?
I'm just wondering.
So for an arbitrary function, the thing is here I've given you the boundaries, so it's for visualization. In reality, you really won't even know, right?
Yeah, because if there's only if you only want to know the center, I'm just wondering.
So I mean, and you're not going to get straight lines, you're going to get curves, so it's always an approximation. Anyways, so now, here's my question. Let's go back to this double pentagon. The network that we saw earlier had 2 hidden layers. Can you compose this using only 1 hidden layer? Anyone? How would you do this with only 1 hidden layer? Yes.
So, well, I would like to ask you a favor there, but first let me try answering this question. My idea, sir, is that each of the hidden units represents if you do the sign many times, and you turn it, so you do it so many times that you turn it into a circle, and then you basically stuff the circles into the shape of the decision boundary.
Okay. Any other answers? We'll hold that thought. Can you do this with just 1 hidden layer?
Yeah.
How?
So each of the neurons corresponds to the same lines that we have, but then you take the AND of the first.
That will not work. Why that will not work is this, right? So you look at this region, this is a 4. The other perceptron, the other pentagon also has some regions where their boundaries will sum to a 4. So you're going to end up with regions outside the double pentagons where the sum is actually greater than the sum inside the 2 pentagons. And so if you do any threshold is going to give you something more than the double pentagon. You can't just do this simply, yeah.
Can we approximate the function with infinite amount of neurons, and we try to get it back to a Boolean?
So you're giving me the same answer that Jeffrey is. Yes.
I think we can do it with single layer, but then weights might have to change.
It's okay. The short answer is these guys are right. You can't do it with a finite number of neurons in the worst case. Let me see how, right? So here, let's go back and try something very simple, a diamond. It has 4 sides. If I have 4 neurons, then the sum of their outputs is going to be 4 inside, less than 4 outside, but the region where the sum is just below 4 is actually infinite area, right? Now, if I use the threshold of 4, now, if I want to be able to compose the double pentagon properly, I want the sum to be really small outside the pentagon so that they don't interact and give me unnecessary combinations. But here I have this very large region where the sum is 4 and our sum is 3. So if I put 2 of these together, the yellow stripes from the 2 diamonds can actually end up giving me a sum of 6, which is greater than even the 4s, right? So what happens if I have 5 sides? Then the region where the sum is 4, actually the area reduces. If I have 6 sides, the region where the sum is 5, just below 6, reduces even further. So that's this figure to the right is showing me the sum of the outputs of the 6 neurons. And you can see it's 6 inside, but then it's 5 for a small region outside, and then you have other numbers. This is what you get with 7 boundaries, a 7-sided heptagon. The sum is 7 inside the heptagon, but just outside you have this 7-sided star where the sum is 6, and then further down you have other areas where the sum is 5 and 4, right? This is with 16 sides. This is with 64 sides. So what do we see as we increase the number of sides? What? Hmm? If I increase the number of sides to infinity, what is the sum of the outputs of these neurons going to look like? With the shape. Eventually it's going to end up, so we can keep working this out. And as I keep increasing the number of sides, the area just outside the central region where the sum is just below n keeps decreasing in size. And so it's actually one of my ideal TAs who worked out this formula for me. And it turns out that as n tends to infinity, the function that it captures is this crazy formula. It's going to be something like a cone which has been chopped off. And as the number of sides increases, eventually even that cone is going to end up looking like a cylinder. The sum is going to be n inside the cylinder and n over 2 outside the cylinder. If I were to, so now, if I were to subtract an n over 2 additionally as a bias, then the sum is going to be n over 2 inside the cylinder and 0 outside. Okay. Once I build this, then I can have one subnet which, so one subnet with a large number of neurons. This is just the sum. I'm applying no threshold, right? And this guy is going to give me a cylinder which is n over 2 here and 0 everywhere else. I can have a second subnet which gives me a different cylinder in a different region and 0 somewhere else, right? If I add up their outputs, what is the result going to look like? This network gives me a 1 inside this cylinder, or n over 2 inside the cylinder and 0 elsewhere, right? This network gives me an n over 2 in a different cylinder and 0 elsewhere. So if I add up these two cylinders don't interact, right? I'm just going to end up with 2 cylinders. And now if I use a threshold, I'm going to get a decision boundary with 2 circles, right? Yeah.
So in essence, sir, so many line decision boundary units a circle make, and if you define many line decision boundary, like if you have many circles, then like you also have like many line decision boundary units, and you can have the circles fill in the DB. In that sense, one layer and then it can like approximate any decision boundary.
Pretty much, right? So this is how you would actually compose this decision boundary using just one hidden layer. You'd have to compose many cylinders, combine them, and is it exact or is it an approximation? But how do I make the approximation more accurate? I reduce the diameter of the cylinders and increase the number of cylinders. I can make the error arbitrarily small, right, by packing them up. And so I can achieve arbitrary precision. So MLPs are universal classifiers. They can capture any classification boundary using just one hidden layer. And they can approximate any classification boundary using just one hidden layer to arbitrary precision. And so we have, again, if I wanted to do this with just one hidden layer, I ended up needing infinite neurons. If I was willing to do this with 2 hidden layers, I just needed 12, right? The difference, again, it's not even exponential, it's just infinite. So that's why you need depth. The deeper the network gets, the fewer the neurons you're going to need, okay? So what is optimal depth? I'm going to look at a different pattern, worst case decision boundaries. I'm going to use threshold activation networks. Consider this decision region boundary I want. I want 1 in the yellow regions and 0 outside. If I were to compose this decision boundary naively, as we just saw, I would need, using one hidden layer, I'd need infinite neurons, right? But I can do this with 2 hidden layers using only 56 neurons. Why so? There are 16 lines. So I can capture the 16 lines with the first, the 16 neurons in the first layer. And then those yellow boxes, there are 40 of those. So I'm going to need 40 of those guys in the second layer. And so this network can once I put in 2 hidden layers, I can capture this decision boundary, right? But then this is just an XOR of Y1 through Y16. So instead of requiring 56 neurons, it's an XOR of 16 elements. So that will need 61 neurons. If I do the XOR with 2 neurons, this is only going to require 46 neurons. So 46 versus 56 doesn't seem very big of a difference. If I do something more complex, a grid formed with 64 lines, then there are 64 basic boundary detectors. There are 544 golden boxes. So with 2 hidden layers, if I just do this naively, it's going to require 608 hidden neurons. But then once again, this is an XOR of those 64 lines. So an XOR of 63 units is only going to require, if I use 3 perceptrons per XOR, it's going to be done with 253 neurons. With 2, it's going to be done with 190. So the difference between 600 and 200 is quite large. But in reality, when you go into higher dimensions, this difference grows very, very quickly, which is why we need depth. So here we are going beyond 2. The XOR is requiring much more than 2, whereas the 600 neurons was done with 2 layers. So even though we are permitting deep networks in both cases, the much deeper network required exponentially fewer neurons, right? Just to give you an idea. So the number of neurons required in a shallow network is potentially exponential in the dimensionality of the input, or exponential in the number of statistically independent features. Okay? And so what we just learned in the past 5 minutes is here in red to add to the story so far. Deeper, a single multi-layer perceptrons are universal classification engine functions. Even a network with a single hidden layer is a universal classifier, but a single layer network may require an exponentially large number of perceptrons, more than the deep one. Deeper networks may require far fewer neurons than shallower networks to express the same function. So in other words, deeper networks are more expressive, right? So let's look at this last topic, universal approximators. We've looked at Boolean functions, we've looked at classifiers, but then what about real valued outputs? We already saw the one-dimensional case. I saw that I can approximate a one-dimensional function of a scalar function of a scalar input to arbitrary precision by simply filling it up with these little, rectangular pulses, right? But when I go into multiple dimensions, you can't just use boxes. That doesn't work. If I go into multiple dimensions, I have to do something crazier. I have to go back to my cylinder networks. I have to compose cylinders, and then each cylinder can be raised to different heights by scaling the output to the height within the average height of the function within the region of the cylinder, and then I sum them up. And so this is how I would approximate a real valued function using just one hidden layer. This is what I wanted to do. So once again, even for real valued functions, I can approximate them to arbitrary precision using just one hidden layer. But then once again, I'm going to need an infinite number of neurons to get it almost right? So MLPs can compose arbitrary functions in any number of dimensions, even with only one hidden layer. And they can do this to arbitrary precision. I can just make the cylinder smaller and smaller and smaller, narrower and narrower and narrower. So MLPs are universal approximators. Now, why is it an approximator? You're not going to get the function exactly. There's always going to be an error, right? It's just that I can make that error arbitrarily small. You give me a limit. You say, I want the error to be less than 10 raised to minus 45. I can give you a network that gives you an error grade lesser than 10 raised to minus 45. It's just going to be incredibly large, but I can always do it, right? So here's your fourth pole. Folks on Zoom, any questions? Any questions on Zoom? No? Okay, this is an easy question. So can somebody on Zoom answer it? Is there anybody on Zoom?
False.
False? How many of you agree that this is false? Why is it false?
Exactly.
It's not exact. It can only be approximated, right? So far, so good. We've seen that MLPs are universal Boolean functions, universal classifiers, universal approximators. So we like them to be deep. We like the networks to be deep, right? Guys, shut your laptops at the back, please. And we like them to be deep because once they become deep, then the number of neurons required, the number of parameters needed by a model is going to be much, much smaller. So what is sufficient depth and what is sufficient width? Now, there's no global answer. There's no way for us to actually know a priori. But just to give you an idea of how this works, let's go back to our problem. Right. The previous discussion showed that even a single hidden layer MLP is a universal function approximator. It can approximate any function to arbitrary precision, but it may require infinite neurons in the one hidden layer. More generally, deeper networks require far fewer neurons for the same approximation error than shallower networks. This is true for Boolean functions, for classifiers, for real valued functions. But there are limits. And so what are the limits? Let's go back to this example where I had 16 boundaries and 40 boxes, right? So if I were to allow myself 2 hidden layers, how many neurons did we require over here? How many did we say we wanted?
56.
We needed 56, right? We needed 16 neurons in the first layer. We needed 40 neurons in the second layer. Now let's assume that I'm going to be using threshold activations. Instead of using 16 neurons in the first layer, if I choose to use only 8 neurons in the first layer, can I compensate for this by making the network deeper? We saw that, we would require fewer than 56 neurons if we let the network go deep, right? But then, suppose instead of 16 neurons in the first layer, I just have 8. Can I just make the network deeper and compensate? Yes.
I don't think so, sir, because I think the idea of the first layer is that it's supposed to represent the edges. The stuff from the second layer are the boxes. The boxes are composed from the edges. If you don't have all the edges, you can't compose all the boxes.
That makes sense to you guys? Right? So what happens is these 8 neurons are going to capture these 8 edges. These are threshold activation functions. The output is 0 on one side and 1 on the other side. So all it can tell you is which of these 8 regions your input lies in, but it's not going to be able to tell you exactly where in that region the input lies. That information has been lost because every neuron outputs either a 1 or a 0. So the information required to compose more of the boundaries is no longer present. If you need, with a threshold activation, you need 16 neurons in that first layer. If you have 1 fewer neuron, you're not going to be able to compose this decision boundary. Now, instead of having them be parallel, if you just decided that those 8 neurons are going to, give you, be differently arranged, like so. Even so, it doesn't really matter. All you will know is in which region of the input space each input lies. But once you get past the first layer, the information required to compose the rest of the boundaries has been lost, right? Why is this happening? Anybody? Why is this happening? Anyone? So, yeah.
I'm not sure, but the input itself is changing the minute you pass through the first layer. So you're not dealing with the same binary outputs, you're dealing with the output of that layer. So you don't have the raw information anymore.
It's a bit of a trick question. Let me explain why. Anyway, before even I continue this, let's go back and look at this problem. Suppose I do have 16 inputs in the first layer, but I just have 40, and I'm still using threshold activations. And instead of having 40 neurons in the second layer, I have a smaller number. Can I get away with it by adding just 1 more layer? Generally can't. We saw that this is an XOR. It needs proper arrangement, right? So not all architectures can represent any function. Regardless of depth, every layer must be sufficiently wide to capture the function if I'm using, but then there's a little escape clause over here. And the escape clause lies in the activation function that we chose. The activation function that I said we were using was the threshold activation. So the threshold activation has this property that, so let's do this in 1 dimension. If I'm doing this in 1, or actually even in 2. So if this is your boundary, the input is here is going to be, so I have my perceptron, I have a bunch of inputs. For any input on this side, the output of the perceptron is going to be 0. For any input on this side, the output is going to be 1. Does the output tell me how far I am from the boundary? That information is lost, which is why all the information that remains is where I am, in which region of the space I am, but you have no more information, right? How can I fix this? Yeah.
Relax the threshold so that it's not a vertical line in the center.
Yeah, someone else was answering in the back here? Yeah.
So like the activation functions and everything in line with your value based on the distance.
You basically, yes. You want the activation function to give you an idea not merely of which side you are on, but how far you are from the boundary. If the activation function gives you this information, now the subsequent layers have some information that they can actually operate on. It's not a blanket case where it will always be successful, but that you have the possibility of actually making up for what was not captured in the first layer, right? And so, for example, if you have a sigmoid activation of this kind, then as you go away from the boundary, the output value actually changes. And so by reading the value, you can get an idea of how far you are from the boundary, and that information can be used to compose additional boundaries. Now for this, the output activation function must carry information about the distance from the boundary. Now, is the sigmoid activation better than the threshold over here? But can we do better than the sigmoid? What is the problem with the sigmoid?
Once it's too far, value can be used.
Can you say that aloud, please?
So once we are too far beyond the point, the values get diluted for all the values.
So once you go beyond this point, then it really doesn't tell you how far you are from the boundary. You only know that you're at least this distance, right? So sigmoid carries information about distance from the boundary for a small distance, after which it sort of dies off, right? What other activation could you use which would be better than this? Like a ReLU, right? So a ReLU continues to give you information about how far you are from the boundary forever on one side, which is why these activations are going to convey more information for downstream neurons, and they can use them to actually learn the function. And in fact, the leaky ReLU is one step better. This gives you information only on one side of the neuron, of the boundary. A leaky ReLU gives you information on both sides, how far you are from the boundary. And so if I had to choose between these guys, the one I would choose is the combination of the red and the blue, right? The leaky ReLU. That making sense to all of you guys? Right. And so narrow layers can still, now there's one more caveat. If somehow the first 8 neurons were all sigmoids or ReLUs or whatever, but their boundaries ended up being like this, you're never going to be able to draw these boundaries. That information is gone, right? So when you use fewer than the minimum number of neurons in any layer, you're still dependent a bit on luck in getting their orientation just right so that you can learn the function better. But with more graded activation functions, you have a better chance of capturing the function. And so narrow layers can still pass information to subsequent layers if the activation function is sufficiently graded. But then you need more depth for the later layers in order to be able to make up for what the earlier layers did not capture. Okay? And so the lesson so far, MLPs are universal function approximators. They can model any Boolean function, classification function, or regression. Deeper MLPs can achieve the same precision but far fewer neurons, but still have sufficient capacity. What do I mean by capacity? The activations must pass information through, and each layer must still be sufficiently wide. Like I said, right? Something of this kind is still going to kill you. So you need enough expressivity within each layer. If you decide that a layer is going to have only one neuron, there's no way you're going to capture a function, right? And so here's the final poll. Okay, guys, can someone on Zoom tell me if the first statement is true? Someone on Zoom? Is that first statement true?
Yes, it's true.
Okay, I gave you the answers, damn. But yeah, the first statement is not true, right? A network with upper bound on layer width cannot model the function if it's sufficiently deep. It depends on, just consider the threshold activations, right? If I say I'm not going to have more than 8 neurons in any layer, that crazy hash could not be modeled, right? Networks with graded activations are more able to compensate for insufficient width through depth than those with saturating or threshold activations. You cannot always compensate for the limits in width and depth by using more graded activations. Again, like in this case, right? If I have 2 neurons, the odds are that I'm not going to be able to capture the full function. For a given accuracy of modeling a function, networks with more graded activations will generally be smaller than those with less graded, saturating or threshold activations. Okay. And so we like to think of the capacity of a network. What can it model? What can a network of a given structure architecture model? And there's been a lot of work, theory, developed on trying to quantify this, things called information and storage capacity, VC dimension, from our perspective, the largest number of disconnected convex regions it can represent, and so on. Regardless of how you define it, here is the bottom line. A network with insufficient capacity cannot exactly model a function that requires, a greater minimal number of convex hulls to actually represent the function, right? You can approximate it with error, but you can never really model it exactly. So lots of definitions for capacity, which I'll skip. So the lessons for today, to stop, MLPs are universal Boolean functions, they're universal classifiers, they're universal function approximators. A single layer, hidden layer MLP can approximate anything to arbitrary precision, but could be exponentially or even infinitely wide in its input size. Deeper MLPs can achieve the same precision with far fewer neurons. Deeper networks are more expressive. More graded activation functions result in more expressive networks. So here's the bottom line. We know MLPs can emulate any function, but how do we make them emulate a specific desired function? For example, a function that takes an image and gives you its label or caption. So for this, we need to train the MLP, and in the subsequent classes, we'll be talking about training MLPs. Thank you.